We are going to do phonons and specific heat capacity for PhD entrance exams. We are going to do a few problems on this topic. This is part 1. So let's get started. And this is the first problem. The first problem is a lattice excitation in one-dimensional lattice has a wave vector k. Show that the corresponding crystal momentum is 0. And you have to use periodic boundary condition. So you have a lattice having, say, identical atoms at the lattice points, and there are n lattice sites. So excitation at a lattice site is given by un e to the power I k na minus omega t. So this na is the position of the lattice site. And since we have identical atoms, so they will have identical amplitudes. So I have taken the amplitude here to be 1. You can take some constant, so because it will be same for all the lattice sites. So the crystal momentum is ddt of un. Again, I have ignored a mass term here. Since all the atoms have the same mass, I have ignored the mass term here. M into ddt of un. And there are n lattice sites, so n will go from 0 to n minus 1. So you have to take a derivative, and it's very easy to see that if you do this derivative and take the sum, so you have to sum over n. You have to sum over n terms. You will get 0 when you use this. This is the periodic boundary condition. This is the periodic boundary condition you have to use at the end. This is the periodic. This is the periodic boundary. This is the periodic boundary condition. Okay, so this you have to use at the end. So next problem is on specific heat capacity. So consider a linear lattice consisting of n identical atoms. Use the Debye approximation, omega is equal to Vk. This is a dispersion relation for the excitation to show that the total energy E of the system is given by this expression. Okay, kBt, so this is given by this entire expression. This we have to show. Okay, in the low temperature limit. This is important. So this is an approximation. Also show that the specificity is proportional to T. So while doing the problem, we can use this, that the average energy of a mode is this. So this is given. So each mode is given by a omega. So the average energy for that mode is given by this h cross omega divided by e to the power h cross omega by kBt minus 1. This is a quantum relation. This is obtained from quantum mechanics, quantum relation using quantum result for harmonic oscillator. So this is a quantum relation. Sorry. Okay, so first number of states. So number of states between k and k plus dk in the wave vector spaces, this we know is L dk by 2 pi. Now this dispersion relation is given, omega is equal to Vk. So from here we can change the variable from k to omega, and what we obtain is d omega. The density of states is given by L divided by 2 pi V. Okay, so if this is true, then density of states. So density of states. So how many density of states or density of modes rather? Okay, density of modes. So this is the density of modes, the number of modes between k and k plus dk. So this is states, or you can say modes, number of modes. So here the number of modes expressed in omega will be L by 2 pi v. So total number of modes we know should be equal to the number of sites, that is n. So d omega 0 to omega d. So omega d is the d by frequency. So this is the maximum frequency that will be excited. This is the d by frequency. Sorry, this is the d by frequency. So from here, if we do this is simple integration, we will get the d by frequency. D by frequency is 2 pi n v by L. Then the total energy of a mode is h cross omega. So we have already know this, average energy of a mode. So average energy of a mode is this into number of modes between omega and omega plus d omega, that is this one. And then we integrate over 0 to omega d, because omega d is the maximum frequency that is excited. No frequency beyond omega d will be excited. So once we do this, then we just substitute my d omega from here, and then to do the integration we have to substitute h cross omega by kbt is equal to x, and this h cross omega t by kb, this has the dimension of temperature. We will call it like this is d by frequency, this is d by temperature. So if you do this integration, you change the variable of the integration from omega to x, then my integration limit will be 0 theta d by t, and then you have the integrand. This you check. So since we are taking the low temperature limit, we will take t tending to 0, and what we will get is, here we will get infinity. So that's how this relation you will get. Okay, so you will get this relation. And the specificity is proportionality, you can easily see, because if you take the derivative of this energy with respect to t, what you get is t. So the specific heat in this case is proportional to t. We go to the next problem. The next problem is for a monoatomic linear lattice of n atoms. Again, this is a linear lattice, one dimensional, of n atoms with nearest neighbor interaction. Show the density of modes is given by this. L is the size of the lattice, pi omega m a omega m square minus omega square. What we know that for a monoatomic lattice, the dispersion relation for excitation is omega is equal to omega m sine Ka by 2. This is the acoustic branch. If you remember the result from monoatomic lattice. So this is given. So this is also not difficult. So again, the number of states or modes between k and k plus dk is L dk by 2 pi. So we have to change it dk to d omega. So for this we will be using this relation. Okay, we will be using this relation. And once we convert dk to d omega, so we will get something like dk is equal to something d omega. So there you will have, here you will have a term like cos k a by 2. This thing will be there. So we have to replace cos k a by 2 So it is in terms of k, you have to write it in terms of omega using this expression. This is simple, and once you write it, you will get this expression, and that you will get the density of modes. So you just have to substitute dk here in terms of omega, and you will get the result. Next, we will show that the free energy of a phonon mode with frequency omega is this: kBt ln twice sine hyperbolic h cross omega by 2 kBt. So how do we do it? So we have to write down the partition function, and this is free energy is written as e to the power minus beta f is equal to partition function. So this is the partition function. Okay, this is the partition function. So we have to evaluate the partition function. So the mode is given by omega. So e to the power minus beta n. N is the various, n defines the various energies the mode can have, or the number of phonons. N basically defines the number of phonons in the mode. Number of phonons of the mode defined by omega, number of phonons. And the energy of the mode is given by n plus half h cross omega. So here we have to substitute it, and that's it, and then you have to sum it. So you have an infinite series which will be pretty simple to evaluate, and if you do this, and from here, what is f? F is equal to minus 1 by beta. Beta is 1 by beta ln z. This is my F, free energy. So calculate Z and you find. So beta, what is beta? Beta is actually 1 by k b t. Okay. Next we go to some this problem. So here some options are given. So which of the following are correct about Debye's theory of specific heat? So you have 4 options. More than one can be correct. So one is solid is a system of coupled oscillators. Does Debye theory consider the solid as a system of coupled oscillators? For a monoatomic solid, the number of normal modes is 3n. N being the number of atoms in the solid. Okay. The 3n modes possess different frequencies up to a maximum frequency. Specific heat at low temperature varies as directly proportional to T, and at high temperature is proportional to T cubed. Now which of these are correct? Now in Debye's theory, this is correct. The system is considered as a system of, the solid is considered as a system of coupled oscillators, which Einstein did not consider. Einstein considered the solid to be consisting of independent oscillators, or de Long-Petit. But in Debye theory, it was considered the solid was considered as a system of coupled oscillators. And for coupled oscillators, there will be 3n normal modes or independent modes, where n is the number of atoms of the solid. So this is also correct. And the 3n modes possess different frequencies. So that there are 3n modes means they consist of different frequencies up to a maximum frequency. Right. This is also correct. What about the last one? Specific heat at low temperature varies as directly proportional to T, and at high temperature directly proportional to T cubed. This is incorrect because device theory only predicts this. Okay, device theory predicts that at a moderate low temperature, the specific heat goes as T cubed. This is the lattice contribution. This is the lattice contribution. The device theory considers only the lattice contribution. This is only due to lattice. This is a lattice contribution, and this T device did not consider. This is the electronic contribution. This you can see at a very low temperature. This is the electronic contribution. For this to see, for you to see this, you have to go to a very low temperature. This is the electronic contribution. This is due to the electron gas. The specific heat goes as T, whereas for lattice contribution, the specific heat goes as T cubed. So these three are correct. The last one is not correct. We go to the next question. So when in a crystal a neutron of wave vector Ki is inelastically scattered to a wave vector Kf, and a phonon of wave vector Ks is created or destroyed, then which of the options is or are correct? Okay, so there you have given a relation between Ki and Kf, and does it mean phonon is created here? Then you have given relation between Ki and Kf. Does it mean phonon is absorbed here? Energy of phonon is given by H cross omega Ks, or none of the above. So here you can write this as, so here this thing can be written as Ki is equal to Kf, the final momentum of the neutron, plus Ks. Ks is the wave vector of the phonon. So this implies that the initial and plus J. So the initial neutron wave vector breaks into Kf and Ks. So this is phonon created. What about this? This can be written as Ki plus Ks is equal to Kf plus G. So what about this? So this means the initial wave vector of the neutron combines with a phonon wave vector Ks to give Kf. So that was what? This is absorption of phonon. Phonon is absorbed. And obviously the energy of a phonon is given by H cross omega Ks. Means this is a dispersion curve. So omega versus K curve will be there for the excitation. So the energy of the phonon is H cross omega. So these three are correct. We now go to the last one. I think this is the last problem. So choose the correct statements for lattice vibration. A one-dimensional monoatomic chain acts as a low-pass filter when nearest neighbor interaction is considered. A one-dimensional diatomic chain acts as a band-pass filter due to frequency gap between acoustical and optical phonon branches. For a crystal with p atoms in a primitive cell, the number of acoustical branches is 3. And next, the last option is number of optical branches do not depend on p. So when we have a one-dimensional monoatomic chain, there is no optical branch, there is only one acoustical branch. So it will look like this. This is my K, this is omega, and so it will look something like this. Okay, so this is my minus pi by a, and this is plus pi by a. So this is the maximum frequency. So all these frequencies till here, so all this frequency can be passed by the solid. So what do you mean by low pass filter? Low pass filter means it can only pass frequencies till a particular threshold. Beyond that frequency, it won't be able to pass the excitation. So low pass filter is, there will be a threshold, only below the threshold all the frequencies will be passed by the system or the solid. So here we have all these frequencies will be passed by the solid. Beyond that, higher frequencies will not be transmitted by the solid. What is a band pass filter? Band pass filter is, it will pass only frequencies within a certain band, and beyond that band it will not pass any frequency. So for a diatomic chain, we know how it looks like. So we have, so here we have similar, we have similar, and for diatomic it will be something like this. Okay, so this is K, this is omega, this is omega. So this is acoustic, this is the acoustic branch, and this is the acoustic branch, and this is the optical branch. This is the optical branch. So this is pi by a. So this is minus pi by a. This is plus pi by a. So you can see, so this is the frequency. So you can see that frequency is still so this solid will pass frequencies in this region, and it's going to, so let me change the color to this, and it's going to pass frequencies in this region. So this is another, so it's going to pass frequencies in this region, and it won't pass frequencies which are in this region. So in this region it won't pass the frequencies. So within this band no frequencies will pass. The frequencies will be passed below this edge, and above this edge frequencies will be passed. So this is a like typical band pass filter. Here we don't have any optical branch because it's a monoatomic solid, one dimensional monoatomic solid. So there will be, so one dimension monatomic, so there is no optical branch. So in general, for a crystal with p atoms in a primitive cell, the number of acoustical branches is 3. That is true. Number of acoustical branches is always 3, and the number of optical branches do not depend on p. This is wrong, because in total there will be, if there are p atoms in a primitive cell, so there will be 3p branches So 3 will be acoustical branches. So 3p minus 3 will give us 3p minus 3 will give us the number of optical branches. Will give us the number of optical branches. So this is not correct. Optical branches depend on P. This is correct, and this is correct. So we'll stop here and we'll meet next time. Thank you.